Genetic algorithms, unlocking optimization through evolutionary computation in an era defined by data complexity and computational challenges. Genetic algorithms stand out as powerful tools inspired by natural selection principles. These optimization techniques mimic biological evolution processes, enabling systems to find optimal solutions through mechanisms like mutation, crossover, and selection. Their ability to navigate vast solution spaces makes them indispensable across industries ranging from engineering design to financial forecasting. As we explore their applications and inner workings, you'll discover how these algorithms revolutionize problem-solving approaches in modern computing environments. The biological foundations of genetic algorithms at their core, genetic algorithms draw inspiration from Darwinian evolutionary theory. They simulate the process of natural selection where only the fittest individuals survive and reproduce. This fundamental concept forms the basis for algorithmic search strategies in complex optimization problems. Like biological organisms, each potential solution in GA maintains a set of characteristics represented as a chromosome. Fitness evaluation determines which solutions will contribute to future generations through reproduction mechanisms similar to sexual selection in nature. The three key operations, selection, crossover, and mutation, mirror evolutionary phenomena. Selection, analogous to survival of the fittest, better performing solutions have higher probabilities of being chosen for reproduction. Crossover resembles genetic recombination during meiosis, combining traits from two parent solutions. Mutation introduces random variations akin to genetic mutations observed in living organisms. This mimicked evolutionary process allows GAs to explore solution landscapes effectively while maintaining diversity within populations. By iteratively improving candidate solutions over successive generations, they achieve remarkable results in various domains. Core components driving genetic algorithm performance. Understanding the architecture of genetic algorithms requires examining their essential components working together harmoniously. The representation scheme defines how solutions are encoded, often using binary strings or real numbers depending on the problem domain. A well-designed fitness function is crucial for evaluating solution quality accurately. It quantifies how close a given solution comes to meeting predefined objectives, guiding the algorithm towards optimal outcomes through selective pressure. Population dynamics play a critical role in determining convergence speed and avoiding premature convergence issues. Maintaining appropriate population sizes ensures sufficient exploration without excessive computation costs. The choice between different types of selection methods significantly impacts performance. Tournament selection offers efficient implementation compared to roulette wheel selection while maintaining good diversity preservation properties. Crossover operators vary based on problem requirements. Single-point crossover works well for discrete representations but may not perform optimally for continuous variables requiring specialized operators like simulated binary crossover, SBX. Mutation rates need careful calibration. Too high introduces unnecessary randomness while too low risks getting stuck in local optima. Adaptive mutation strategies help maintain balance during different stages of evolution. Algorithm workflow and implementation process. The execution flow follows a structured sequence ensuring systematic exploration of solution space. Initialization begins with creating an initial population of randomly generated chromosomes representing diverse starting points. Fitness evaluation measures each individual's effectiveness against target criteria. Selection then identifies promising candidates for breeding based on relative fitness scores calculated during assessment phase. Crossover combines selected parents' genetic material to produce offspring with mixed characteristics. Mutation introduces small random changes to maintain population diversity and prevent stagnation. These steps repeat iteratively until termination conditions are met. Criteria such as reaching maximum iterations or achieving acceptable fitness levels determine when to stop further computations. Implementation involves translating theoretical concepts into executable code. Programming languages like Python offer robust libraries supporting GA development through frameworks such as DEAP, distributed evolutionary algorithms in Python. optimization parameters require tuning for best results. Population size, mutation rate, crossover probability, and other factors demand empirical testing to identify ideal values for specific application scenarios. Diverse applications across industries' manufacturing sectors benefit greatly from genetic algorithms in optimizing production schedules and facility layouts. For example, automotive plants use GAs to minimize assembly line idle times and maximize throughput efficiency. Scheduling problems become computationally expensive as task dependencies increase. In healthcare settings, hospitals apply GAs to optimize nurse shift assignments while considering both staff availability and patient care needs simultaneously. Logistics companies leverage GAs for route optimization challenges involving hundreds of delivery locations. FedEx and UPS employ these techniques to reduce fuel consumption and vehicle maintenance costs associated with inefficient routing patterns. Financial institutions utilize GAs for portfolio optimization tasks aiming to maximize returns while managing risk exposure. Portfolio managers use these algorithms to balance investments across various asset classes according to investor preferences. Risk management professionals apply GAs in developing hedging strategies that mitigate market volatility. These techniques enable more accurate predictions of price fluctuations under different economic scenarios. Engineering disciplines find extensive uses for GAs in structural design optimizations. Aerospace engineers use these algorithms to create lightweight yet strong aircraft structures that meet safety standards while minimizing material usage. Architects incorporate GAs in building design processes to optimize energy consumption patterns. Smart buildings developed using these techniques demonstrate improved sustainability metrics across multiple environmental indicators. Beyond traditional fields, creative industries also adopt GAs for artistic purposes. Digital artists use these algorithms to generate novel visual patterns and music compositions through evolutionary aesthetics approaches. Case study: optimizing supply chain networks using genetic algorithms. A multinational consumer goods company faced significant challenges in its global supply chain network. Excessive inventory holding costs combined with frequent stockouts created operational inefficiencies costing millions annually. By implementing a custom-built GA system, the company successfully optimized its distribution center locations and inventory allocation strategies. The algorithm evaluated thousands of possible configurations daily, identifying cost-effective solutions previously unattainable through manual analysis. Results showed a 28% reduction in total logistics costs after 6 months of implementation. Warehouse utilization rates increased by 35%, leading to substantial savings from reduced rent expenses at existing facilities. The most impactful change came from dynamic pricing strategies enabled by GA-driven demand forecasts. Inventory turnover ratios improved dramatically, reducing obsolete product accumulation in storage areas. This case study illustrates how properly implemented GAs can transform complex business operations. The success relied heavily on integrating domain-specific knowledge into the algorithm's design rather than relying solely on automated processing. Challenges and limitations in practical implementations. Despite their power, genetic algorithms face inherent limitations that developers must address carefully. Premature convergence remains a common issue where suboptimal solutions get trapped early in the evolutionary process. Computational resource demands grow exponentially with increasing problem complexity. Large-scale industrial applications often require parallel processing capabilities beyond basic hardware configurations. Parameter sensitivity poses another challenge since minor adjustments can lead to drastically different outcomes. Finding optimal parameter combinations usually requires extensive experimentation guided by domain expertise. Interpretability difficulties arise from the black box nature of GA solutions. While effective, the evolved strategies sometimes lack clear explanations understandable to human decision-makers. Overfitting risks emerge when algorithms memorize training data instead of generalizing useful patterns. proper validation procedures must accompany every implementation cycle to detect such anomalies promptly. Integration complexities appear when embedding GA modules within existing software architectures. Compatibility issues frequently occur due to differences in data formats and communication protocols between systems. Scalability concerns limit applicability to very large datasets without proper architectural considerations. Distributed computing paradigms become necessary for handling massive problem instances efficiently. Advancements and future directions in genetic algorithm research. Ongoing research continues pushing the boundaries of what genetic algorithms can accomplish. Hybridization techniques combine GAs with other metaheuristics to overcome individual methodological shortcomings. Recent developments include incorporating machine learning elements to enhance GA performance. Neural networks now assist in feature selection and parameter adaptation phases, accelerating convergence speeds significantly. Cloud computing platforms provide new opportunities for distributed GA implementations. Parallel processing capabilities allow tackling larger problem instances within reasonable timeframes previously deemed impractical. Quantum computing integration represents an exciting frontier. Quantum-inspired evolutionary algorithms promise faster convergence and better handling of combinatorial optimization problems through superposition principles. Multi-objective extensions of classical GAs handle trade-off scenarios more effectively. Techniques like NSGA2 enable simultaneous optimization of conflicting objectives, providing Pareto frontiers for informed decision-making. Self-adaptive GA variants modify parameters dynamically during execution. These intelligent systems adjust mutation rates and selection pressures based on real-time feedback from evolving populations. Ethical considerations gain prominence as AI technologies advance. Researchers increasingly focus on ensuring fairness and transparency in GA-generated solutions, particularly in sensitive domains like criminal justice and hiring practices. Practical tips for developing effective genetic algorithms. Successful GA implementation depends on several foundational considerations. Understanding constraints and objective functions shapes the entire algorithm design. Selecting appropriate representation schemes is crucial. Binary encodings work well for simple problems but may struggle with continuous variable domains requiring alternative encoding strategies. Designing meaningful fitness functions takes precedence over choosing other parameters. A poorly formulated fitness measure leads to misleading optimization trajectories that fail to reach true minima/maxima. Tuning parameter settings through experimental trials proves more effective than relying on default values. Systematic variation of population sizes, mutation rates, and crossover probabilities reveals optimal configuration patterns. Implementing elitism preserves top performers across generations, preventing loss of potentially valuable solutions during evolutionary transitions. Monitoring convergence behavior helps identify premature stagnation. Early detection enables timely intervention through parameter adjustment or algorithm modification strategies. Testing with benchmark problems establishes baseline performance metrics before applying the algorithm to actual industry cases. Comparative analyses with alternative optimization methods highlight strengths and weaknesses objectively. Conclusion: genetic algorithms represent a transformative approach to solving complex optimization problems across various domains. Their evolutionary foundations enable innovative solutions that conventional methods often cannot achieve. While presenting unique challenges, these algorithms offer unparalleled flexibility in navigating multidimensional solution spaces. Continued advancements ensure their relevance in emerging technological landscapes, making them invaluable tools for tomorrow's algorithmic innovators.